So today we are going to start uniting electricity and magnetism. We've already kind of seen some hints here and there about the fact that they may be somewhat connected. And it is going to turn out that there's really only one field, the electromagnetic field. And whether you see it manifested as an electric field or as a magnetic field is really just a matter of your perspective. So one person might see an electric field, another person might see an electric and magnetic field, one might see a magnetic field. It just depends on how you're looking. Now, we already pointed this out when we originally introduced the idea of a charge makes an electric field, but a moving charge also makes a magnetic field. So there, it seems to be that it's just a matter of perspective. And one of the ways we got around that was by saying, well, the thing that we normally look at making magnetic fields is current, because current is kind of like having our cake and eating it too. It's moving charge, so we can make a magnetic field, but wires usually have a net charge overall of 0 because the moving charge has accompanied with it equal and opposite other charge. So we can say that for wires, we don't care about their electric field because there's no electric field, but it does make a magnetic field. So we're going to delve into that further today and actually make this connection. And let me remind you that the big difference between what we could see electric fields and magnetic fields doing is that an electric field can accelerate a charge from rest. So an electric field has no problems taking a stationary charge and making it go faster. What we say if we want to be fancy is that the electric field can do work. So it can change the kinetic energy of a particle. That's just a fancy way of saying it can change its speed. Whereas what we've seen in the magnetic field, we've made a big point about saying it's deflective only. If the charge is already moving, it can deflect it into a circle or a helix, but it can't make it go faster or slower than it was going before. It can just change the path. The magnetic force plays this role of a guiding force. If you want to be fancy, you can say that the work done by the magnetic field is 0. It does no work. It can't change the kinetic energy of motion. So it can deflect it, but it can't make it go faster or slower. So now what I'd like to do is show you kind of the classic thought experiment where I show you how intimate a connection these two things have to each other. And it's not going to just be a theoretical thing on the board. I actually have the apparatus here with me so I can show you in person that it really does work as advertised. So here's my situation. I'm going to take a bar magnet and I'm going to take a conducting ring. That conducting ring is not made out of any kind of magnetic material. The only thing that has to do is be an electrical conductor. And so my first scenario, I'm going to suppose that both the magnet and ring are at rest as far as my opinion is concerned, relative to me. I'll draw a subset of the magnetic field that is made by the bar magnet. I'm not going to draw the full loops. We, of course, talked about the fact that magnetic field lines always form closed loops. But I don't need to draw the magnetic field everywhere because I'm really just concerned about the bar magnet's effect on the ring. So I'm going to draw the relevant portion of the magnetic field of the bar magnet where the ring actually is. Okay? So what we see, if this is a conducting ring, there will be charge carriers inside it. They're, of course, really electrons, but we, of course, typically, just for convenience, think of them as positive charges. So there will be free positive charges inside that ring, just waiting for some kind of thing to do. Now, in this case, will they do anything? They will not. The charges in the ring are at rest with respect to us. And what we learned, of course, is that if you're at rest, a magnetic field can't pick you up and make you go faster. It's deflective only. So the charges that are in the ring stay at rest. So nothing happens. If the charges were already moving, then the magnetic field could deflect them into a circle, a helix, or whatever, but they're not moving at all. So nothing happens. So you can't just hold a magnet next to a conducting ring and expect something to happen in the ring. We're going to have to create some motion. So let's do that. So what I'm going to do in this case is I'm going to create the motion by moving the ring toward the magnet. I'm going to keep the magnet at rest. It's the ring that's going to be moving. So I basically said same perspective here. Something like this. And let's re-examine. So now I have a charge here. Let's put a charge here. And by virtue of the fact that I'm moving the entire conducting ring, that of course means that I'm taking all of the charge carriers that are in it and moving them in the magnetic field. So now we have some motion that the magnetic field can do something about. So now we can have the charges be deflected. So now that they have some pre-existing motion, there can be some kind of deflection of them. So let's employ the right-hand rule. This is definitely going to be awkward, long slaps. But I'll show you a much, much easier shortcut to do this, probably even a little bit later today. So I point my fingers along V, and I have to orient my palm so that I can slap V all the way into B. So pretty long slap here, V into B. Okay? It's almost 180 degrees, right? So remember to do it with the palm of your hand, V slapped into B, so the force will be into the page. And again, if you find that challenging, I'll show you there's a shortcut even later today. So the magnetic force on this particle is going to be into the page. And so if this charge is sitting at the top of the ring, it will not stay there for long. It will be deflected such that it goes onto the back side. It'll kind of go like this. It'll flow onto the back side, right? Let's do it again for the charge at the very bottom. And I'm basically just cherry picking the ones that are going to be easiest to look at. V goes like this, and I have to orient my palm so I can push V into B, which is a long slap. It's almost 180 degrees. The force is out. So the force on this one will be out of the page. And so if that's the charge carrier that's sitting at the very bottom of the ring, it won't stay there for long. It'll flow out of the page, which means onto the front of this thing. And we notice something interesting is that both of these deflections actually agree that the charge should be moving in a certain circular direction on the ring. And the current actually starts to flow on the ring. So what we have here is that, to summarize, we move the ring, and then the magnetic field deflects the charges and by the way, what's the motion of these charges ultimately going to be? Well, they're circulating around the ring, and the ring is also moving forward. So what is the ultimate path of these charges? It's just a helix. It just happens to be going on inside a ring. Okay? So deflects charges, they actually form a helix from your perspective. But if we're just talking about what's going on inside the ring and not worried about the ring moving forward as well, we might say this causes an induced current. So the reason why we call it induced is, of course, we didn't create this current with a battery. We connected it by waving this conducting ring in the region of a magnet. So we've somehow induced it to flow just by moving the ring here in a magnetic field. So here, the induced current is not 0, whereas over here, of course, it was. So nothing too remarkable about that. We're just putting magnetic deflection for good use. Okay? We're using this idea that when charges move, the magnetic field can deflect them into a helix, and we're usually using that to generate a current. So, let me set this up for you. You can actually see it. So I have bring this thing out. So here's what I have. Here's my ring. It's actually not just one ring, but as usual, we put a bunch of rings, put a bunch of turns just to exaggerate the effect. Okay. And how am I going to tell if there's a current in there? Well, I literally have this connected up to this big giant ammeter, which, by the way, I brought in that one that my students had made. This is just a slightly more kind of professional version, but you can see here there's a current loop and there's a big needle attached to it. So what we get to, this will deflect if we can get some current going in there. Now the difference here is, of course, there is no source of current except I'm going to make the current by introducing a magnet. So let me bring in this magnet. It's a very powerful magnet. Okay. It's a powerful rare earth magnet. I've made it even more powerful by taping light poles together, which is a very dangerous thing because light poles really don't like to be together. But I've taped the north and the north together to make a super north, and a south and a south together to make a super south. Okay? So it's a powerful bar magnet. And so what I'm going to do is exactly this. I'm going to have the bar magnet, I have my ring, or in this case really a bunch of rings. And the way I'm going to tell if this induced current is there or not is you can see the needle move from 0 on the ammeter. Now first things first, let me just put the magnet in there. It's a powerful magnetic field in there, but you see no current, right? And the reason why is that no matter how powerful the magnetic field, it can't just pick up charges from rest. It's deflective only. So what we need to do is we need to move the ring relative to the magnet. So let's try that. So you should see that the needle moves. Oh, but this looks not quite 0, so let me 0 it. Okay. And you should see, I'm going to do this. I'm going to move the ring away and towards the magnet, and during the time that it's moving, we're going to see that the magnetic field is able to deflect charges into a current. So watch the needle. Significant, right? In fact, I hit the very end of it, so it kind of bounced. So, right, you can see when there's motion, we get a current, right? It takes a while to settle back down. This doesn't have very good damping. But whenever the loop is moved towards or away from the magnet, we can deflect the charges into a current. Okay, so no big deal. Well, the final step, what if I reversed who is moving and I do this instead? I have that the ring itself is stationary, but I move the magnet. So we seem to have arrived at a little bit of a situation. Because to us, the charges in this ring are at rest. And we've learned that if a charge is at rest, the magnetic field can't deflect it, right? There's nothing to deflect, right? So by that logic, the induced current should be 0. And yet, in another way, you might say, does it really matter if it's the ring moving towards the magnet or the magnet moving towards the ring? Common sense should dictate, right, that it should, as long as they're moving relative to each other, you should get this induced current, right? So let's try it. Go to this thing, and I'll move the magnet instead. And of course, we do get that while the magnet's in motion, we get an induced current. So we appeal to this idea that all motion is relative. That, by the way, was what Einstein developed into his theory of relativity. And of course, we get an induced current that is not 0 here too. But then we're left with the uncomfortable notion of what is the flaw in our equations, because the magnetic force here should be 0 because the charges are at rest. It's deflective only. So we're only left with one type of field. What's the kind of field that can pick up charges from rest? Electric field. So we've suddenly created an electric field. So this is an electric force that picks up the charges from rest. Picks up charges from rest, and that is in fact what causes the induced current. And by the way, it'll be exactly the same direction as it was in the previous example. I induced goes like that. So hopefully you see that this simple demonstration is meant for us to reckon with the fact that there is a huge amount of intertwinedness between electricity and magnetism. And which type of field you see is really just a matter of your perspective. In this particular situation, our explanation for why the current flows is magnetic force. In this one, our explanation is electric force. And all the difference is which one we imagine moving and which one we imagine staying at rest, and yet we're forced to come up with different conclusions. In this one, it's purely magnetic. There's no need to invoke anything unusual, but here we have to, seemingly out of nowhere, it's an electric field that will pick up these charges from rest. So, what's going on here? Here's how I would characterize it. We said that charges create electric fields. That was the starting point, first couple lectures of the class. Then we said moving charges create magnetic fields. So charges that we think are moving. And then finally, to kind of close out the circle of logic, I'm going to say that quote-unquote moving magnetic fields create electric fields. So you can see that one kind of begets the other, or when you think it's one thing in one perspective, it's the other in somebody else's perspective. So this last kind of hub of the wheel, this right here, will basically be what homework number 7 is all about, is to explore this relationship. And I should characterize this a little bit. We won't really call it moving magnetic field. In fact, moving magnetic field is a little bit of a weird term. That's why I put it in quotes. A better way to think of it would be time evolving, right? So the magnetic field experienced by this ring will change with time if you start waving the magnet. Okay, so it's basically a better way to think of it would be a magnetic field that changes with time. It turns out that you can even relax the restriction more from there. Anytime there's a magnetic flux that evolves with time. And of course, what the heck flux is something that we need to discuss. So that'll be one of the things that is definitely pretty immediately on our plate. And then the other thing is that while this does create an electric field, rather than talking about the field picture, we've of course learned that the voltage picture is oftentimes a lot easier to use. So instead we'll characterize this as an EMF. So for instance, when you guys did circuits, right, the EMF was the voltage of the battery, right? So you connected a battery up to things and it caused current to flow. Well, we're going to have circuits where there's current that flows and yet no battery in sight. The thing that drives that current is not a battery, it's a changing magnetic flux. So we're going to be able to cause current to seemingly flow out of nowhere by changing this thing called magnetic flux. It's another way to generate electricity. So the thing that connects these two, and notice that this does connect electricity and magnetism. The EMF is the electric thing, and the magnetic flux is the magnetic thing. The thing that connects these two is called Faraday's law. And that is basically the major, I should say, this is basically the single equation that will be featured on homework 7. Of course, you can flip it around a bunch of different ways, and I'll show you all that. That's going to be our law for connecting electricity and magnetism. The only thing we have to get out of the way first is I want to show you some trick for getting the directions. Now, these long slap rules that we did here, obviously those were challenging. And here it's even unclear how you would execute a slap rule because from our perspective, these charges are at rest, so there's no velocity to slap into anything. So I want to show you a rule of thumb that will get you the right answers. It'll be a lot easier and broader way to get the right answers for what happens with the current. Okay? So this new induced current, how do you get the direction of it? Then Faraday's law is what we'll pick up next, which will allow us to figure out how big is that current. Okay? So, are there any questions before I move forward? Okay, so let me show you this rule of thumb. This is called Lenz's law. So Lenz's law is basically a way to find the direction of the induced current. And the best way I would describe Lenz's law, it's a status quo law. So if you don't know what status quo means, what that means is trying to keep things the same. Okay? So this law, the way to remember how it works is that it wants to keep things from changing. It doesn't want things to increase, it doesn't want things to decrease, it just wants things the way they already are. Okay? So here's the way to think of it. It fights all change. So let's say, for instance, I had a B external that was like that, and this was constant in time. So constant in time. So there's nothing that changes about that, and so Lenz's law is happy. It says, okay, that's fine. And so what happens is there is no induced current. I guess I'll put it over here. So there's nothing to fight if there's nothing that's trying to change. However, let's say, for instance, that B external points like this, and it's increasing in time. Well then, Lenz's law kicks in and says, I would prefer that you didn't increase. And so now, the induced current is not zero. It's going to fight that change. Now, how is it going to fight that change? Well, let me remind you that whenever you have an induced current, that will make its own magnetic field, right? If I have a current that flows like this, that makes a magnetic field through the core like this, right? So here, what's going to happen is that B induced, that magnetic field made by the I induced, is going to point opposite like this. So it wants to fight the change. And what you can do is you can infer what does the direction of I induced have to be to make that. Okay? So that's the part that everyone seems to be able to remember. But remember that it's not going to be opposite just to be opposite. It's opposite because this is increasing. If this was constant in time, there wouldn't be anything to fight. And likewise, if B external is like this, but it's decreasing, again, I induced is not going to be zero, because there's some change to fight. But now, it doesn't like decreases either. So now the B induced is going to be in the same direction. So it's not always opposite. Sometimes it's zero, and sometimes it's with the external field. It's whatever would most fight the change. So it tries to fight increases by opposing them, being opposite to that, but it also tries to prevent decreases by putting a magnetic field back in the original direction. See, it's a status quo law, right? It doesn't allow things to change. Does that make sense? So anytime that you try to do something with the external field, B induced will fight that change, and you can work backwards to what I induced must be to make that B induced. So, for instance, if you go over here, of course, there is no change to fight because the magnetic field that this ring feels is constant in time. I'm not saying it's uniform. The magnetic field over here might be weaker than over here or something, but it's not changing with time. So that's why nothing flowed here. I'll clear that one off. I guess let me copy this one since this is that was already pretty cluttered. So let me move the magnet toward the ring. So this is my B external. So as far as the ring is concerned, that is the magnetic field that it's exposed to from outside. So, as far as the ring is concerned, if you bring the magnet closer, is the B external going to increase or decrease with time? Increase, right? This is going to increase with time. You're bringing the magnet closer, so you're going to expose the ring to a stronger field. Okay? So, if we go over here, which way does B induced want to point to fight that change? To the left. So B induced wants to point like this. And then we use our right-hand rule, working backwards, right? Current is going to flow like this if the B induced through the middle is going to go like that, right? So I induced points like that. So we've just figured out in a much shorter way, not having to do these awkward slaps, although I will point out it's the same direction we found before, right? That's the same as this and same as this, okay? So it's a lot easier. All right? So now that I've shown you that it does produce the same answer, let's delete these guys and move forward. One of the things we might do, of course, just to make sure we can do this, is try the other case. Let's say we have that the bar magnet is moved away. So instead of pushing the magnet towards, we pull the magnet away. So the magnetic field is like this. Of course, the magnetic field lines leave the North Pole, so the magnetic field that is external to the ring is still pointing generally in the rightward direction. But now, of course, if we pull the magnet away, what happens to the strength of that field is felt by the ring. It's decreased. Right? So if it's decreased, which is the direction of B induced? The same way, right? It wants to not allow that decrease, so the current's going to flow like this. So now the current reverses direction, so that B induced can reverse direction. So that now it's trying to prevent the decrease instead of trying to prevent the increase. So that's my claim for what happens. The induced current will flow around opposite directions depending on whether I bring the magnet closer or further away. So I'm going to now show you this. I have a ring just like these. I can untangle them. I don't know what happened here. There we go. So I have this ring. And one of the things you may notice is, of course, there's no ammeter in sight. So the question is, how am I going to convince you that, one, there is current flowing in there at all, and number two, that it is in the direction that I've advertised? Well, there will always be some kind of macroscopic, see with your own eyes manifestation of Lenz's law. You don't need an ammeter, you can just look at it and see. So Lenz's law often, or most of the time has a see with your own eyes thing that you can do. Let me show you what it is in this case. This is where we can remember that if we cause a current to flow around, then we've essentially made that look like a magnet, right? So if the magnetic field induced comes out of here and then goes back in here, well, this is the North Pole and this is the South Pole. As long as there is current flowing in that ring, it will have magnetic poles. Remember, the magnetic pole, north is where the magnetic field lines come out, and south is where they go back in. So I'm not going to need an ammeter for this. If I try to bring this magnet closer, this simulates a magnet where the north is on the left and the south is on the right. What's going to happen with this north and north? They're going to repel. So there's literally a see with your own eyes. This ring does not want this magnetic field to come in. And it will literally move away when you try to bring it closer. Alright? So let's go over here. Well, now the current's going the other way. The magnetic field's induced is coming out of the right side, and so this is going to be our North Pole, our virtual North Pole, and this is going to be our virtual South Pole. So clearly, this object is not a permanent magnet, because if you switch the current direction in it, you'll switch the magnetic poles. Now, if I try to pull this away, the north and the south are closest to each other. What's going to happen there? It's going to attract. That's how I'm going to know that everything is as advertised. So if I go over to this ring, first of all, let me try to convince you that it is not magnetic material. It's not inherently magnetic. So this base is a powerful magnet. But this is not. Okay? There's nothing inherently magnetic. It's not magnetic material. But it becomes a magnet when I induce a current in it. And so what you're looking for is when I shove the magnet toward it, the induced current will have some temporary magnetic poles that repel it. So it's Lenz's law in action. So watch carefully here. Did it move away? Okay, I'll try it again. It's a subtle effect. But when I put the magnet in there, for the duration of the magnet moving, this will have an induced current and it will repel. So you should see it move away when I put the magnet in there. Yes? Okay? So, let's try the opposite. When I try to pull it out, it should attract. So, let's try it. It attracts, right? So, think of it like this, right? As I'm putting this magnet in, the induced current flows like this, and the magnetic field comes out like this, so it creates a north pole on this side. But when I try to pull it out, the induced current flows this way, and the EB induced points to the right, and then the north pole is on this side, right? So see with your own eyes, it doesn't like to change flux, right? It doesn't want to allow this magnet to get closer, but once the magnet is closer, it doesn't like to have it go away. So I can get a pretty good swing going on here, because of course this thing wants to repel when I'm bringing it towards it. Oh, didn't mean to touch it. Right? And I can pull it. When I pull it away, it tracks. Okay? So the best analogy I can give for this, if you've ever been in one of those dysfunctional relationships, right? Stay away, no, don't go. Stay away, no, don't go, right? Status quo. Nothing ever seems to change. Okay? I can also try this other ring, which is seemingly exactly identical. Whoa. I can get it off there. I'll try with this one. Nothing happens. The reason why is it literally has a little break in it. So current can't flow because current can't circulate all the way around. See that? So it literally is just current flowing around the perimeter of the ring. And which way it flows will depend on whether or not I'm bringing the magnet closer, it doesn't like that, or I'm trying to take the magnet away, it doesn't like that. It's a status quo law. So, let me try it with something besides a bar magnet. Let me try it with this thing. So this is an electromagnet instead. So here's what we have. There's a solenoid here. So of course we learned that a solenoid can create a large magnetic field in its interior. And if you're neck close to the front of it, it'll still be pretty strong. And it also has this magnetic material. And of course what we learned is that if you apply a magnetic field, and you send current around the solenoid, that's going to create a magnetic field like that through the core, and that's going to actually magnetize this material, and its magnetic field will get added on top, right? So this is just basically a way to suddenly, from no magnetic field, generate a large magnetic field if I just turn on the current. So let me put a conducting ring here on this thing, and I'm going to turn on the magnetic field very rapidly, and we should see some repulsion. So this thing is called a ring launcher, for obvious reasons. Another way that you may have heard of this being put to use is something called a railgun. So this idea that this thing really doesn't like to change, the magnetic field it experiences, so it will create magnetic poles to repel. I can try this with various things. Let's try to compare this one, so I'll get a sense of how high that flies. Okay, that touched the ceiling beam. Let's try this one. Doesn't go nearly as high, even though it's actually less weight. The reason why is because if you want to carry a lot of current, you have to have very little resistance. So we learned that one of the things that determines resistance is cross-sectional area, right? This one is a nice 5-lane highway going around like this. It's nice and wide, whereas this one is a much more narrow path, and so current has a harder time flowing in it. And if there's less current, less I induced, these magnetic poles won't be as strong either, right? I can try other stuff. Let's throw in this one. It has a break in it. It's not going to work at all. Can't carry an induced current. Try this one. Nothing happens. This is pretty much a very high insulator, so it doesn't matter that it's contiguous because its resistivity is so high, right? I can try, what else? I can try this one. This is a current loop that has a light bulb attached. So I can make the light bulb light up. Okay? There's no battery in here. All I did was take the induced current and have it do the thing that we normally have it do, have it flow through a light bulb, right? So that's another way to light up a light bulb is instead of attaching it to a battery, we just do something with the magnetic field nearby, right? Right? So there is some fun with the ring launcher. Any questions on that? Okay. So that's Lenz's law in a nutshell, and it's something that's a really nice thing to hold on to as we start to move into Faraday's law, because it's a really easy way to just think through what is the induced current direction going to be. The induced current is going to flow such as to fight changes. If there are no time evolving, there's nothing changing in time, there's nothing to fight. But if the magnetic field tries to increase, it'll go against it, and if it tries to decrease, it'll go with it. I should mention that homework number 7, I think the whole first half of it is just Lenz's law stuff. Okay, so no calculations of any kind, just using Lenz's law to figure out does the induced current flow this way or that way. So I want you to really get some practice doing this. You'll also get some practice doing this in your lab on Faraday's law, where you'll use Lenz's law a bit as well. Okay, any questions before I move forward? All right, so let's go ahead and now talk about Faraday's law. So Faraday's law I'll just go ahead and write it down first. It looks like this. Now, obviously, some new stuff going on in there, but I do want to point out that on the left-hand side, there's your EMF. That EMF is every bit as real as the EMF made from a battery, but it's not an EMF made from a battery. This electrical phenomenon is due to the fact that over here we have magnetic flux changing with time. So there you see the connection between electricity on the left and magnetic stuff on the right. So we already said there had to be some evolving with time, so it's reassuring to see time in there. And then, of course, this new quantity is called magnetic flux. So obviously, before we can even crack this law, we have to talk about what's magnetic flux, then we can come back to understand this law. But before I even do that, I want to point out that once you have this EMF, go ahead and just use Ohm's law to connect that EMF to the induced current that will flow. So once you have a certain EMF, you also have to consider if you have a small or a big resistance before you know how much the induced current will be, right? So if you get a certain amount of EMF, but it's through a highly resistive thing, you'll get barely any current. And vice versa, you'll get a lot of current if your resistance is very small. So of course that's why we saw the metal rings jump so high off the ring launcher, and the rings with brakes and highly insulating things not really much at all. Okay. So we have use for our good old Ohm's law, like usual, but we, of course, the EMF is from a completely alien source. And the reason why there's absolute value signs here is that we really just use this to get the amount or size of the EMF. The direction is going to be Lenz's law. Lenz's law you're going to use to get the direction of the induced current. So in a certain sense, Lenz's law is really just part of Faraday's law. Okay? So Lenz's law helps you get the direction for Faraday's law, and Faraday's law, as we call it, is really just helping us calculate the actual amount of current. Okay?